Hello everyone, I am Geeta welcoming you all to this session to discuss about instruction format and reduced instruction set computing. So in this session we will just discuss about the instruction format. So as we all know, when we write an high level language program, it is going to be translated into machine code, and for translation it needs the instruction format. So the instruction set architecture plays a major role in the computer to translate the high level language code into a machine code. So for that we have to understand what is the format of the instruction to be followed. So if we take any format, any instruction for that matter, the three important components of an instruction will be, so we have the opcode, okay. So what is the operation to be done? So that is specified by opcode, and this operation to be done on some data. So where this data is going to be available, we will be specifying the address of the data. So that will be the second important information, and apart from this we will also provide the mode, okay. So what we mean by mode is, the mode specifies the way in which the effective address is going to be calculated for the operand. So if you take any instruction for that matter, it is going to comprise of three important fields, okay. The first one is going to be the opcode, okay. So that's what opcode here, it is going to specify what is the operation to be done. Suppose for example if you want to do add, okay, so I will be specifying add, this will specify the operation, then on what this add operation has to be done. So where the data is available, it can be available in the memory, or it can be there in the register, or it can be immediately supplied along with the instruction. So where is the whereabout of this data? So that address, so the address field, so here we will be specifying the address add a comma b. That means it can be a register or it can be memory. So where the address is available. So one part of the instruction will be the opcode, another part of the instruction will be the details about the address of the data, and then this and then we will specify the mode, okay. The purpose of having the mode is we will be either following some direct addressing scheme or indirect addressing scheme. So how we are going to calculate the address of these operand? Is it going to follow a direct method or indirect method? Is it going to involve the base addresses or scaling addresses, like that? So the details about how to calculate the effective address of the operand is going to be specified by mode. Anyhow, at this point of time we need not get confused with mode. So the only understanding to be made for this mode is that how the effective address is going to be calculated for the final operand. So that is specified by the mode. So any instruction for that matter is going to have three important fields. One, the mode used to calculate the address of the operand. Next one is the opcode, that is going to specify the operation to be done, and third one is the address, which tells about the whereabout of the data. Now if you take an opcode, if it is going to be m bits, so this is going to be the instruction format. If I say that the opcode is going to have m bits, that means at the maximum with m bits I can perform 2 power m combinations. So I can perform 2 power m operations on that particular instruction set, and that is what I have mentioned here, 2 power m. And then if the register, the address you have, and if I allocate k bits for the registers, that means with k bits I can address 2 power k different combinations, okay. So there could be at the maximum of 2 power k registers. Suppose for example in a CPU, if it say that the CPU is going to have 16 registers, then how many bits are required to address these 16 registers? How I will be calculating? This is nothing but 2 power 4. So with 4 bits I will be able to address 16 registers. So if you take an instruction, the number of bits reserved for the address bit will decide how many such locations can be addressed. So if I reserve k bits for the address bits, then 2 power k locations, different locations can be addressed, and that is what I mentioned here. So if you have k bits as an address, then 2 power k registers can be numbered, and it can range from R0 to Rk minus 1, R0 through Rk minus 1. Just for example, they have taken a CPU with 16 registers. So if the CPU is going to have 16 registers, obviously 4 bit will be more than enough for me to address each of the registers. Suppose for example, if my register is like this 1010, then what is the register which is going to address, which is going to be addressed here? It is going to refer to R10. So I can address any register numbered from R0 to R15, and all these numbers can be represented with just 4 bit of information, and this information will be occupying the address field. So whenever we start programming a particular processor, we should be familiar with the instruction set architecture, and that instruction set architecture only will decide how many bits to be allocated for opcode, how many bits to be allocated for address of the operand, and it can be referring to the memory address or it can be referring to the register address, all decided based on the configuration of the processor. If I say it is an 8-bit processor and it supports 16 registers, then I should reserve 4 bits to address any one of the registers. And now coming to the computer instruction address, okay, so the instruction format, we can have some classifications, namely it can be a 0 address instruction, 1 address instruction, 2 address instruction or 3 address instruction. So what actually we mean by this? So where we have the operand, we have to specify the address of that operand. If the instruction itself is going to carry the operand, I need not specify any address, so in that case it will come 0 address. So when, under what situation we will be having 0 address? If we know that the data is going to be available in the stack, I need not give any address. Why? Because the stack pointer is already pointed to that address. So I need not explicitly mention any address. So in such case, it will be covered as a 0 address instruction. And sometimes if it is going to refer accumulator for one operand, another operand I don't know, it can be in register or it can be in memory. So in that case, the second operand address, either the register name or the memory address, if that is to be specified, I am just specifying only one address in the transaction, so it will come under the category one address. And sometimes two operands can reside in the memory. If 2 operands are going to sit in the memory, I have to specify 2 different addresses, so in that case it will come under the category 2 address instruction. And under what situation we will be facing 3 address? So I will be giving 2 address for the memory operand, that is a source operand. After performing the operation where the result has to be transferred, again if I want the result back in the memory, then I have to specify 3 address. So 2 address for the source and 1 address for the destination. So in such cases it will come under the category 3 address instruction. So where the data is available, if it is there in the stack, no need to specify address, it comes in the first category. If the data is there in the memory or in the register and one data is there in the accumulator, then it is enough that I will specify address of the operand which is there in the memory or in the register, so it will come under 1 address. So in 2 address I will be specifying the 2 sources, and in 3 address I will be specifying the 2 sources and the 1 destination. So based on this category under which how I specify the operands in the instruction, so we will classify the following types. So we will just see each of this type one by one with an example. So as I already discussed, any instruction having opcode field, address field and mode field, these 3 are going to be the important 3 components of any instruction, okay, and the length of the instruction is going to vary and it depends on the number of addresses it is going to follow. So if it is going to be a 3 address format, it has to specify 3 addresses. So accordingly the length of the instruction also will keep varying. Now the CPU organization, how it is going to be organized, we can classify that into 3 types, okay. So based on which the number of address fields it is going to include. So one classification is 0 address, 1 address, 2 address and 3 address. Another classification is it will refer to where the data is available, okay. If it is going to be there in the single accumulator, it is single accumulator organization. If it is going to be stored in the registers, it comes under the second category, general register organization. And if you are going to store the data in the stack, which is going to be a special memory, then it is going to be called as a stack organization. So in this session we are going to discuss about the classification of CPU organization based on the number of addresses it is going to involve, on which it comes under the classification 0, 1, 2, 3, and based on where we have the data, either it could be in accumulator, it can be in register or it can be stack. Accordingly we have these 3 classifications. So first we will just see one by one. So we will just take the example of accumulator based organization. You all know accumulator is going to be a special register which will accumulate the results, okay. And in the second type, general register organization, we will have so many registers available. So these registers will store the data and these registers will be used for all the computations of the intermediate results. And the third organization is going to be the stack, which will always refer to the stack for referring the data, okay. So we will just see one by one and we will just see the example for 0 address instruction. So we are going to take a common expression x is equal to a plus b star c plus d. So this is what we are going to evaluate, and we do not know where the a, b, c and d values are going to be stored. If they are going to be used in the registers, it will come under the category general register. And if all these operands are going to be stored in the stack, it will come under the category third one, stack organization. Or one by one, if you are going to make use of accumulator and one operand in memory, it will come under the first category. So we are going to discuss all these three type of organizations with respect to this expression, namely a plus b star into c plus d. So the first one is zero address. So when we will have zero address, if we know the whereabout of the operands, if the operand is stored in the stack, we need not explicitly mention the address, no address is required. Why? Because the stack pointer is always going to point to the address, so I need not bother about of specifying the address in the instruction. So whenever I am going to make use of the stack, it will be a very good example for zero address instruction. So in this case, we are seeing that a plus b star c plus d. Okay. So first to start with, what we will be doing, pushing a, it will push a into the stack, push b, the second operand also will be pushed into the stack, and now we have to do the addition operation or subtraction, whatever it could be. Now if I just apply the operator, obviously the two operands will be popped out from the stack. I will apply the operation a star b, and that result again will be pushed into the stack. So whenever I am doing like this, I need not mention the address of a, the address of b, because we all know the stack pointer is always pointed to the topmost location of the stack, which is nothing but the operand a, and the next one will be the operand b. So since we need not mention any address here, it is going to be an example for zero address instruction. So a stack based computer, if the computer is going to be based on stack, it will not use any address field in the instruction. And to evaluate the expression, first as I told, we have to convert the expression into Polish notation or postfix notation, reverse Polish notation or postfix notation. So the given expression is a plus b star c plus d. So maybe I will write it, for example, again already we have discussed the same expression, a plus b star c plus d. So the first operation to be done is ab, so that will be plus, and then the second one should be c plus d, so cd, then it will be plus. And once I get the result for the first one and the second one, these two should be multiplied. So the second operator, the last operator is going to be the multiplication. So this is going to be the conversion of the given infix expression into a reverse Polish notation form. And once that is given, then I can just simply make use of the stack itself. Now we will just see the different lines of code that are to be executed to solve this expression. Now what is the first one we will do? We have to push this into the stack. So push a, that means stack, we have the stack here, and of course the stack pointer will be pointing to this location, it is 0, and whenever I want to push something, it will be incremented, I will be pushing a, and this first location will be having this data. Then the next one is operand. So whenever we encounter operand, it has to be pushed into the stack. So increment the stack, I will be pushing that, okay, it will become 2. And then we encounter plus. So whenever we have operator, we have to pop the two most element from the stack. So take out b, take out a, apply the operator plus, okay. So I will get some answer a plus b. So now what will be there in the stack? So again the stack 0 will not be used, it will be initialized here, stack pointer will be incremented, I will be pushing the answer a plus b. So in the stack I will be getting the data a plus b. So after adding, the topmost element will be a plus b. So the answer for a plus b. Now you just scan the expression, it is c, it is an operand, so you will be pushing into the stack. So stack pointer will be incremented and I will be pushing c. Then I encounter d, so again you will be incrementing the stack pointer, so it will be 3 and you will be pushing d. Now what happens? I have plus. Plus means I have to pop the two most operator, first top two operators. So top two operator is c and d, so I will take out d out and then I will take out c, okay. Then I will apply the operator plus, okay. So I will get the answer c plus d, so that will be pushed into the stack. Now how the stack will look like? So already the 0th location will not be having anything, already we have a plus b, it is not going to be disturbed. The top two elements will be popped out, so as and when I pop out, the stack pointer will be incremented and then it will be showing this next location and then this location. Now the stack pointer is here, I have to push the value c plus d, so c plus d will be pushed here and this is going to be the first location, stack pointer will be pointing to this information. And then I have the last operator star. So again, whenever I experience an operator, I have to pop the topmost two elements of the stack. So C plus D will be popped out, and then I will be popping out A plus B. See, on these two popped out elements, I will be applying the operator star. I will be getting the result. So the whole result will be again pushed back into the stack. Now what will be there in the stack? 0, and the result of A plus B star C plus D. So the final outcome will be pushed. And since there are no more operators available in this expression, that's it. I have completed the evaluation of the expression. So whatever is there in the stack, that will give me the answer. So this is going to be an example for stack based organization where we expect the operand to be stored only in the stack. And here, after doing this mull operation, again we will be pushing, the result will be pushed into the stack, and when we pop out, you will be getting the final outcome of this expression. So this is an example, or the code, the lines of code which are required to solve this expression in zero address format. So push A, push B, add, then push C, push D, then add, then we have to multiply. And after performing all these things, I have to do pop. Only if I do pop, the last value will be obtained outside, and it will be available in topmost of the stack, and that will be moved on to the memory wherever you desire. Either you can move it to memory, or you can move it to data register, or any register for that matter. So this is how the expression is going to be evaluated on stack based organization. And if you just observe each instruction, none of the instruction is referring to address, no address is mentioned. See, only push A, push B, all these things add. Add what is to be added, I don't specify. Why? Because it always have to refer to the stack only. And in stack, what is items to be referred? The topmost two element. And how I will refer that? By means of stack pointer. So no need to mention address in any of these instruction, and hence this is going to be a very good example for zero address instruction format. Now we will just proceed, we will discuss the same example with respect to one address instruction. So in one address instruction, what is the format of the instruction? So we have the opcode which will specify what is the operation to be done, and we have to specify one address. Okay, so the address of one operand has to be mentioned here. So that will also occupy some portion in the instruction. So we will reserve some space in the instruction format to store the address of the operand. And what is the mode in which we are going to calculate the effective address? So that is going to be specified in the third component called the mode. Okay, again we are going to take the same expression, and if it is going to involve one address, how the code is going to look like. Okay, so now here it is no more stack, it is going to refer only to memory. AC is accumulator, and M is any memory location, and M of T means some temporary location reserved. Okay, so now I have memory, and it is not a stack now, it is going to be organized in first in first out fashion, whereas in stack it is LIFO, here it is FIFO. Now we will again take the same expression, A plus B star C plus D. So A, first I have to get A, so load A, I will be referring to load A. Load A means memory will be having the values of A, B, C and D. It will be having all the values available in the memory, and I hope you all know this is going to be the portion called data segment. So some portion of the memory which is designated as data segment is supposed to handle all the data. So the data will be available in the memory, and I don't know the address. Okay, so whatever is address of that operand, that will be referred, and that will be moved into accumulator. So load A, if I give like this, what will happen? Accumulator will be loaded with the data A. So this data is available in the memory. Okay, so only we have mentioned it as M, and who is giving the address? Some A. So when I execute this instruction load A, I will be loading one data into the accumulator. Then add B. So directly I can add with the memory content. So if I just say add B, what will happen? One operand is expected in the accumulator. Okay, so accumulator will be having the already preloaded operand, that is nothing but A, and then I am going to directly add with B. So accumulator is in turn going to have the value A. A and B will be added, and the result will be stored in the accumulator. Okay, so now what happens? I have just done A plus B, and the answer is available in the accumulator. Now I have to perform another operation. So to perform another operation, again I need accumulator. Accumulator is having the result, I should not disturb it. So what should I do? I should move the result back into the memory location. So whatever is there in the memory, that should be stored in some temporary location. So I will give store T. So when I give store T, what will happen? the accumulator content will be moved into the memory location. Because I am going to use accumulator for other operation, I should preserve the answer. So whatever I have calculated now, a plus b, that is going to reach the temporary location. So again in memory there will be some temporary location reserved for that purpose, which is pointed by the address t, and now this will have the value a plus b. Okay, so these first three instruction helps me to perform the first addition a and b, the result stored in memory in temporary location. Now what should I do? I should move on to c. So load c. So if I say load c, what will happen? Accumulator will be initialized with the c. Then what should I do? I have to add with d. So directly I will do addition, add d. If I give this instruction, what will happen? Accumulator will be already loaded with c and that will be added with d. So c plus d will be available and it will be made in the accumulator. Now what should I do? That accumulator content has to be again moved into some memory location, or I should start with multiplying the previous outcome. So directly after adding, what should I do? I will just say mul. So what should be multiplied? Already the temporary location is having the answer a plus b. So m of t mul t. Simply I will give t. So if I give t, what will happen? Accumulator will be referred with accumulator multiplied with memory and pointed by the temporary location, which is going to have me the intermediate result a plus b. So a plus b will be available here and accumulator will be having the already calculated c plus d. So c plus d will be available in accumulator. So these two will be multiplied. So the final outcome will be made available in the accumulator. If you want the accumulator, you can refer the result directly from the accumulator, or for future purpose you can store again the accumulator value. So if I give store some address, then in that address the answer will be moved on. So whatever is the final outcome of this arithmetic expression, that will be moved into the memory location. Now if you observe all these instructions will refer to memory with one address. Address for A, address for B, address for C, address for D, and here it will refer to address for the temporary location, and again it refers to address of the X. So in all these instructions, it will refer to only one address of the operand. Another address need not be mentioned because it is referring to the accumulator for another operand. So if in each of the instruction, if you just observe, accumulator is also referred. Accumulator, we need not mention any address or any information. So all these going to be an example for one address instruction. So the next category is two address. So in the two address, what we will be having, each instruction will carry two address. Okay. So most of the cases, the two addresses will be the direct memory address of the operand. So that we will again see with the same example or with the same expression how it is going to be interpreted. Now we have the opcode here, the destination address, the source address and the mode. So as I told, we have to mention two addresses, okay, the source address and the destination address. So either we will be having two operands, in that case we will be referring to two source address, or if it is going to refer only one operand in memory and one operand for storing the result, then these two addresses will be mentioned. So where the source is available, where we have to store the result, and what is the operation to be done, and what is the mode of operation. So in the instruction format, here it varies. So in the previous case, in the 0 address, no address is there, just the opcode alone is mentioned. Whereas in one address, I will be specifying one address. In this two address format, I have to specify two addresses, two locations has to be reserved for address. Obviously, the length of the instruction is going to increase here. Now, what is example? Again, we take the same expression a plus b star c plus d. How we are going to get things done with the help of two address. So the first example is, first we have a plus b has to be multiplied with c plus d, and we all know the memory is going to have some data for me. Okay, here one destination address, one source address, only one information will be referred in memory, another one will be the destination address. So what I am trying to do, I am just going to load register 1 with a. Okay, so move r1 comma a. So here refers to the address in the memory. So what is the address in which I will be having the first data, or the data for the address for the data a. Okay, so that will be moved into register 1. So register 1 will load the first data, and then what I will be doing, I will be giving add r1. So add r1 directly, I can add it with b, which is there in the memory. So first instruction will move the data into register 1, first data will be moved into register 1, and I am going to directly add with b. So when I execute this, what will happen, r1 is going to have the previous r1 added with b, and of course R1 is going to have the data A. So A plus B will be added and it will be made available in R1. So after doing this, what should I do? I should preserve it, or I should keep the value of A plus B somewhere in the memory, okay, or in the register. So since I have enough number of registers in the CPU, I am not going to preserve it somewhere. Let me keep it in R1 itself. So I am not going to disturb. R1 is going to have me the value for A plus B, okay. Now I will start proceeding to C plus D. So first I should take C from the memory. So I will be moving R2 with the C. So R2 register will be loading with the data C. And then what I should do, I should directly add with D. So what I will be doing, add R2 comma D. So if I gave like this, what will happen? R2 is equal to R2 plus D. Already R2 is having C, C plus D will be made available in R2. Okay. So now what is that I have to do? C plus D is available in R2, A plus B is available in R1. So these two registers, now what should I do? I should multiply. So directly I will just say multiply R1 comma R2. If I give like this, what will happen? So one of the destination address is nothing but R1. So R1 will be equal to already previously stored value of R1 multiplied with R2. So now what will happen here? I will be having the answer for A plus B, which is in R1, and C plus D, which is in R2. So these two registers are going to be multiplied with a star, and the answer is again going to be stored back in the first register, namely the R1. And now if I want to store the result in some memory location, then I can use move R1. R1 is going to have the answer. So to what location I have to move, I can specify the address here and then get that answer. So this completes the evaluation of the expression A plus B star C plus D, which involves two addresses, one for the memory and another for the register address. So this is how this operation is going to happen for solving A plus B star C plus D. So the next example is a 3 address instruction, okay. So we have opcode, the destination address, okay, and we are going to refer two operands. So one is going to be the source address 1, another one is source address 2, and then how we are going to calculate the effective address of the final operand, that mode. So now if you just observe this category, the instruction format itself is going to be lengthier because it is having opcode and it has to mention 3 addresses, 2 source addresses, each referring to individual operand, and then one destination address, and then the mode of calculating the effective address. Now if you just see the example, the same example, A plus B, then star C plus D. So in each instruction itself we can specify 2 address for the operand and 1 address for the destination. So what I am going to do, I am going to refer A, B. So these two are going to be added, add A comma B, and I can also mention one more address where the result is supposed to be in the same instruction itself. So I will be just saying that add R1 comma A comma B. If you just give this single instruction is referring to all the possibilities. So what happens here, R1 will be equal to A plus B. So it refers to the two data, the source address 1 and source address 2, and then the result has to be stored in the destination address R1. So A plus B stored in R1. And then after completing this, I have to refer the second one. So it is going to be again another add C comma D, and it may refer to the second register R2. So now what will happen, R2 will be having the summation of C and D. After performing this, what is it I should do? I know the answer, one operand is in R1, another operand is in R2. So these two operands are now going to be connected with the star operator. So I will be using mul, okay. So what to be multiplied? I have to multiply R1 and R2, and so far we will just seen that the result is going to be stored again back in the source. Now if I want to have a separate location in the memory to store the result, that address can also be given here. So if I just say like this, what will happen, R1 final content and R2 final content will be multiplied, and the final outcome of the whole expression is going to be made available in X. Now if you just see this example, we have only 3 lines to complete the code. Whereas in the previous example, if you just see here, we 1, 2, 3, 4, 5, 6 instructions are required to complete the task. Whereas again, if you just move on to the previous topic, there also for 3 plus 3, 6 plus 1, 7 instructions are required. Whereas in zero address instruction format, still more number of instructions are required because push and pop is there. So 1, 2, 3, 4, 5, 6, 7, 8. So here to solve the same expression for each type of organization, the number of lines required to solve the problem is going to vary because how many times I refer the memory, how many times I do the transfer. So that also always matters. So far we have discussed four different instruction format. One is zero address, which will always refer the operand in the accumulator or which will always refer the operand in the stack. Then one address instruction where only one address will be specified, another will be implied, and usually it will refer to accumulator. The third one is register based organization where it will refer one operand in register, another operand can be directly accessed in the memory or it can be stored into some register and then we can carry out the transaction. And when it comes to the last category, namely the 3 address instruction format, we will be specifying 2 address, one for the source 1, source 2 and another address to store the destination. So all the 3 address will be supplied along with the instruction, which increases the length of the instruction, but the number of lines in the solving the problem is going to be minimal. So obviously there is a trade-off. If I reduce the number of instructions, then the instruction size, the length of this instruction will be increased. Okay. So far we have discussed about 0 address, 1 address, 2 address and 3 address. So in the next session we will continue with single accumulator based CPU organization and general register organization. Hello everyone, welcoming you to all to discuss the topic about single accumulator based CPU organization. So in the previous session we have discussed about the different types of CPU organization, namely stack organization, accumulator based and general register based organization. As a continuation of the previous topic, what we have discussed is the different types of instruction format based on the number of addresses. So the instruction could be a 0 address instruction, a single address instruction, 2 address instruction, 3 address instruction. What actually we mean by these addresses is that whenever we are referring to the operand, how many addresses are going to specified in the instruction. In the 0 address instruction, we assume that the operand will be in accumulator or in the stack. It is an implied operand. Whereas in a single address instruction format, one address will be given and that will be referring another operand either in the accumulator or in an implied storage unit. In 2 address instruction format, so we will be referring to source addresses, two source addresses, source 1 and source 2, and the destination will replace any one of the source. And coming to 3 address instruction format, we will be having reference to 2 single source and 1 reference will be to the destination. So that completes the discussion of 0 address, 1 address, 2 address and 3 address. So in today's session, we will continue with a single accumulator based CPU organization. So here we have only one address field and that address field specify one of the data and the remaining data will be always referring to accumulator. That's what we mean by single accumulator. So because of this situation, this CPU is sometimes also referred as one address machine if it is going to follow single accumulator based CPU organization. So the main important points to be considered in this type is that in CPU based organization, the ALU operand is always stored in the accumulator. So accumulator will always be referred to one of the source and another operand will be referred in the memory or it can be in the register. So the two possible locations is it can be in the register or in the memory. So one address will be specified and that address will be referring to either register or to the memory. And usually accumulator will be the default address and the results are also again accumulated back in the same register. And the format of this instruction will be, so you will be having the opcode. So as we all know, the opcode will specify what is the operation to be done and one operand will be in accumulator. Another operand address, it could refer to either register or it could refer to memory. So the second operand could be either in the register or in the memory. After performing the operation, the result is also again expected to be stored in the accumulator. So usually this type of instruction will be performing the arithmetic operation in this format. So it will be storing the result in accumulator and it will refer one of the operand in accumulator. So for that we need not specify any address. The next operand will be either in the register or in the memory. So in the instruction, we are going to specify the address about the register or the memory and only this address is going to be specified in the instruction and so only it is called as single address instruction. or one address machine. So in accumulator based organization, what we have to remember, accumulator is going to get one operand and the result will be again stored back in the accumulator. So the two types of operation usually performed in single accumulator based CPU organization is the data transfer operation and the ALU operation. So coming to data transfer, as I told here, if you refer one of the operand in register, that register address itself can be given and another operand should be in memory. So when we execute this type of instructions in accumulator based organization, we expect one operand to be in accumulator. That means accumulator has to be initialized with the data. So we all know the data will be there in the memory. So there could be some separate instruction to be used, executed to move the data from the memory to the accumulator. For that type of operation, we refer as data transfer operation. So memory will be having the data and the address to which we are going to refer is going to be referred by the register AR, and this data has to be moved into accumulator. So this is to supply the input operand. After performing the arithmetic and logic operation, the accumulator is expected to have the result, okay, and this result has to be again stored back in the memory. So as far as the data transfer is concerned, we need to move the data from the memory to the accumulator or from the accumulator to the memory. So we need two type of data transfer operations to be handled to deal with the accumulator based CPU organization. So one such type is called load. So what we mean by load, load is nothing but read. So this is going to be the load. I am just going to refer the memory and read the information and store it in accumulator. So here load is also referring to read, and actually what happens in load operation is the accumulator will be initialized with the data available in the memory pointed by the address register. So we are referring to memory for the data and the address will be available in AR that will be moved into accumulator. So this is what we mean by load operation. The other way, when we want to transfer the result back to the memory, then we will be using the instruction called store, or this can also be referred as write. Write means I am going to write into the memory. So in memory, address pointed by AR, I am going to move the content of accumulator. Here from accumulator, if I move something into the memory, this is called as write operation, or this is also called as store operation. And when I move the data from the memory to accumulator, this is called as load operation, or it is also called as read operation. And the another important operation that is going to be performed in accumulator based CPU organization is the ALU operation. And as we already know, for ALU we expect one operand in accumulator. So an example here given is mult x. Okay. So what actually we mean by mult x? So it is going to refer to accumulator for one operand, and the operation to be done is multiplication, and another operand will be in the register x. So the answer will be again stored back in the accumulator. So in all the single accumulator based CPU organization, we expect one operand to be in accumulator, another operand could be in either register or it could be in memory. And after performing the operation, the result is again expected back to be in accumulator. So this completes the discussion of single accumulator based organization. Okay. So we will also discuss about this type of CPU organization. Actually, accumulator based CPU organization, it is supported or implemented in PDP-8 processor. A very good example of this type of organization is PDP-8 processor, which make use of this type of organization. And coming to the advantage and disadvantage, one of the operand is always held in the accumulator, and hence the results in the short instructions will consume only less memory space, because we are going to refer to the memory for only one operand. Already one operand is moved into accumulator, so obviously it will consume less memory space as far as the instruction is concerned, because we are referring only to one address in the memory. And the instruction cycle time, if you take, it will also take minimal amount, because it is going to fetch only one operand from the memory. Of course, there could be an argument to load the accumulator, we have to refer to the memory that consumes some cycle, but it is done in a separate instruction. So any arithmetic and logic operation will refer to memory for only one operand, and for that it will consume only less amount of time. So that's a claim that has been identified as a advantage of this type of organization. Coming to the disadvantages, when we are in need of computing some complex expression where we need so many operands and so many operators, then obviously the program size will increase, because we are going to make use of only short instructions. Every instruction needs the data to be loaded in the accumulator. For that we have to introduce one instruction. So if an expression is going to involve some complicated or lengthier operands, all these operands have to be individually loaded into the accumulator, then only we can start doing the actual operation. So this may be consuming memory. You have to understand this properly. In advantage also we have claimed that it consumes less memory space, and it may be a contradicting process here. Here they claim that the memory size increases. So you have to understand in the sense that if it is going to have minimal number of operands, if I load that operand in the previous instruction, in the coming instruction I can just refer only one operand in the memory, so it consumes less space. If the expression itself is complicated in nature, that involves multiple operands, for each of the operand I have to load into the accumulator, I have to clear the accumulator, or if the accumulator is already having some intermediate results, it has to be stored in some memory, then only I can load new operand into the memory. So this may take extra memory. So when it comes to a complicated instruction, definitely the memory size will increase, and this is going to be the drawback claimed by this type of organization. As the number of instruction increases for the program, obviously the execution time also may increase. So at one perspective, we are claiming that as an advantage of consuming less time and consuming less memory space. The same thing is going to be a drawback if it is going to involve some complicated operations where it is involving multiple operands. So we can recommend this type of organization if the expression is going to involve simple operation or minimal number of operands. So next we will discuss about the next type of organization, that is nothing but the general register based CPU organization. So this is usual concept. So we are going to refer to register based. So any processor will have its own set of registers. So how many multiple general purpose registers are available, that decides the efficiency of this type of organization. If many CPU registers are available, then we need not store the intermediate results anywhere, we can store everything in the registers itself. So it can minimize the number of memory references, because we have enough number of registers, all the intermediate calculations could be stored in the register itself, and so I no need to refer to the memory. So if the number of registers available for me is very minimal, I have to update the memory for frequent storage, for intermediate storage. So in such cases it will be a problem. Okay, so the execution speed, the program execution speed is always dependent on the number of registers available. If more number of registers are available, I can store all the results in the registers itself. So I can avoid memory reference. So whenever I am able to avoid memory reference, execution time can be minimized. So we will just take one example here, multiple R1, R2, R3. So we are going to refer 3 registers. There is no restriction on the number of registers in this case. So we are referring all the 3 registers. So R2 and R3 is going to be the source. I am going to multiply these two, and the product is going to be stored in R1. Since we have enough number of registers, we are storing the result back in the register itself. If there is a limitation in the number of registers, I have to store the result into the memory. So this could be avoided here, because we have no shortage in the registers, number of registers available. So use of large number of registers will end up in a short program. Why short program? See, in one instruction itself I am able to implement the entire operation. No need to load, no need to store. So we are able to minimize the number of instructions. If this load store architecture is adopted, we have to use one instruction to load the operand. After performing the operation, you have to store the result again in the memory. So it may involve some 3 instructions, whereas in this case with single instruction I am able to implement the whole operation, because I have enough number of registers. So whenever we have large number of registers, the program size is going to be minimal. If the program size is minimal, obviously the memory space also will be minimal. And if the registers are already having enough data for me, I am able to skip the memory reference, and whenever I am skipping the memory reference, obviously I can reduce the execution time. So that's what will be claimed as a advantage of the general register organization. So efficiency of the CPU will increase if there are large number of registers, because no intermediate storage required, no need to transfer back into the memory, and whenever I am minimizing the memory reference, I can reduce the time taken. And less memory space will be used by the source program because the instructions are written in a compact way. So these are the two advantages that we are going to claim from the register based organization, and if we have enough number of registers, we can always have these advantages applicable. Then coming to the drawbacks, care should be taken to avoid unnecessary usage of registers. Okay. So if we keep on using all combination of registers, then the complexity will be loaded on the compiler part. The compiler needs to be more intelligent. Okay. So why? Because it has to optimize the utilization of the number of registers. If more number of registers are available, just like that we will make use of the registers and it may not be effectively utilized. So to optimize the usage of the number of registers, the compiler has to take the burden, and hence the compiler will need to be expected to be an intelligent one in order to handle this sort of situation. Since large number of registers are used, extra cost is required. Obviously, this is an obvious statement because whenever we go for large number of registers, it demands hardware security, and obviously that hardware security will end up in an expensive expense. It will be of costly in nature. So we have discussed the general register based organization. In register based organization, we expect all the operands to be there in the registers, and we will always refer two registers to refer to the source and one register for the destination. And if we have enough number of registers, we can always claim the advantage of making the memory effectively utilized and also CPU time minimized. And coming to the drawback, because we avoid unnecessary usage of registers, the compiler has to be more intelligent. So we expect the compiler to take the burden. And another important point is, whenever we demand higher number of registers, obviously it can increase the hardware security cost. So extra cost may be required for this type of organization. So we have discussed stack based organization, accumulator based organization, and then we have also discussed the general register or register based organization. Actually, this general register based organization may be classified under two categories. One is register memory reference, another one is register reference. So what we mean by register memory reference, as the name implies, one operand will be in register, another operand could be there in the memory. So that means source 1 is required to be a register, and source 2, it can be a register or it can be a memory. Okay, one of the operand is expected to be in memory. So in that case, source 1 will always be expected in register, and source 2 either it can be in register or it can be in memory. So if this format is followed, this will come under the first category. Next category is both are registers. That means I am totally neglecting the memory reference. So ALU operations are performed only on the register data. When I prefer this type of operation, for this particular instruction, definitely the time taken to execute the instruction will be minimal. So operands are required or expected to be loaded in the register well in advance before executing the instruction. After calculation, the result will be again back stored in the register itself, and the address instruction format is very much compatible when we consider this type of category. So to illustrate the influence of the number of addresses and the type of organization, I think better we can analyze all these classification with respect to an example. So we are going to take an expression x is equal to a plus b. Actually this equal to is not there, it is a plus b. Okay, you can just avoid this, you can just skip this, a plus b into c plus d. So to do this to calculation, we need to use add instruction, sub, multiplication, division, and sometimes we need to move the data from the memory to the register. So we will be using move, that is to take care of the transfer of the data, and then we can use load and store. So these are the various instructions that is going to be involved in calculating the expression a plus b star c plus d, and the result has to be stored in x. Okay. Now if I want to execute this with a 3 address instruction, I think we have given an example here. So our intention is to execute x is equal to a plus b. This should be done first, then I have to do c plus d, then I have to multiply. So this is going to be the first operation, the second operation is c plus d, and then I will be performing the multiplication. So the multiplication will be the last operation. So for each of these operations we need to write separate instruction. So first one is a plus b. So add, I am going to do add, and what is to be added? A and b. So I will be referring to a and b, and the result has to be stored somewhere. It is going to be a register based organization. So one storage will be register. So what will happen? R1 will be initialized with the data available in memory location pointed by A plus the data available in the memory location pointed by the address B. So it will perform the first operation. So the first operation is going to be implemented with the help of this example, and then we have to proceed to C plus D. So add R2 comma C comma D. So here I am using one register, another I am using another register. So if enough registers are there, then this sort of limitation will not be there, and we will be getting the result of C plus D in R2. So this is nothing but the equivalent operation of the second category. Then after performing the summation of A, B and C, D, that has to be multiplied with each other. So R1 content, that is the first data, which is nothing but A plus B, and R2 content, which is nothing but the second instruction, that is C plus D. So this A plus B and C plus D will be available in two registers. So these two registers has to be multiplied with X. Okay. So here what I actually mean by X, the result is going to be stored in the memory, and whenever I store the result back in the memory, in which address it has to be stored, so that has to be specified here. So this instruction is going to refer to one address, and it is going to refer to two address for the register. So any arithmetic operation for that matter, you all know the destination is nothing but the source 1, then whatever the operator you want to do, that you will be doing, and then the source 2. So what sort of combo is going to be followed for S1 and S2, that only dictates this type of classification. So in this general register based organization, what they have told, source 1 is always expected to be a register, and coming to source 2, it can be a register. If it is a register, it will come under the second category, register reference. So this is going to be the second classification. Sometimes what it could be a memory also. So if it is going to be memory, I have to specify the address of the memory where I will be getting the data. So this is going to be the first category. So in any of these two categories, I will be able to perform the operation once I am ready with the data for one operand in the register. Okay. So this completes the discussion of the expression evaluation A plus B star C plus D, and this is for the 3 address format. So whenever we are using 3 address, a single instruction itself will be enabled, will be able to handle both the inputs and also store the result back in the destination. So whenever we adopt 3 address instruction to implement this operation, it's enough that with 3 instructions we will be able to do the exact operation. Now the same thing can be compared if it is going to adopt 2 address instruction format. So coming to 2 address instruction format, here we have A and B. So we have to load it into R1. So A will be moved to R1 and B will be moved to R1. So we will be adding with B and the result will be stored in R1. So here what happens, R1 will be initialized with R1 and whatever is there in the register B, so that will be added, and already R1 is moved with A. So A plus B will be added and this will be moved into R1. Okay. Then the next expression C plus D. So first we have to load R2 with the data C. So this will be done, and the second instruction will be able to perform the second operation, namely C plus D. So here C plus D will be done and this will be moved into R2, whereas in R1 it will be adding A and B and storing the result. After getting the results, summation results in R2 and R1 and R2, then we will be able to do the multiplication operation. So for that we issue the instruction mul R1 comma R2. As the name implies, it will refer to registers for the sources and it will replace the first source with the destination. Then after completing all these operations, I expect the result in R1. So R1 is supposed to have the data. This data has to be stored back into the memory, and again where it has to be stored, that address will be supplied in the instruction as X. That means R1 will have some data. So R1 is now expected to have the data of A plus B. Here it is A plus B, here it is C plus D. So C plus D will be available in R2 and R1 will be having A plus B Now my intention is to multiply R1 and R2. So multiply R1 and R2. After performing this, as we already mentioned, either you could supply the address of the result, or you can replace one of the source. So in this example, what they have done, they have replaced one of the registers. So mul R1 and R2 it is having, and now the result R1 plus R2 is again back stored in R1. So that means R1 register, which is already having this A plus B, will be no more. And the last instruction will be helping me to transfer the result available in the register R1. So this has to be transferred into the memory whose address is pointed by X. So this is what the actual operation to be done. So if I just want to summarize this, so I will be performing A plus B, and this will be stored in the register R1, and then I will take C and D, and this will be stored in register R2, and then I will be multiplying R1, R2. So I will be prefixing with the instruction mul. Okay, so it will multiply R1 and R2, and again the result is expected to be only in R1. R1 is equal to R1 into R2. After doing this, what we are going to do, we have to store the result back in the memory. So the R1 is expected to have the answer. So we will be using store. So what to be stored, it is available in accumulator. Where to be stored, that is available in the register 2. So store R2 will help me to store the final result. So this completes the discussion of this two address. And then single address. So more or less single address is also similar to the previous case. So here in single address, I am just going to refer to only one address, and that address will be always referring to memory. So if you want to initialize accumulator with the data, I will be using the load instruction. If you want to transfer the data from the accumulator into the memory, then I will be using the store instruction. So to start with, the first data will be loaded in accumulator. So if we just trace here, what will happen? We have accumulator, and then we have the memory and address pointed by X. Okay. So here what are the various possible values initialized to X. If you are clear with this, then the rest of the instructions or the programming part will be more clear. So the first instruction, what it is performing, M of A. So wherever I have a location A, so I will select that particular data, and that is going to be loaded into the accumulator. So first data 1 will be loaded into accumulator. Then what we are doing, add B. Okay, so B is already having some data. Okay, B is available in the memory and it has some location. So I can refer to that location directly by specifying the address. So now what I am trying to do, I am just going to do the next operation, that is C plus D. So before getting into C plus D, the intermediate result you have to remember, the intermediate result obtained in the temporary storage purpose, it is stored in the memory pointed by T. So in memory we are going to refer to 3 locations, 2 locations for A and B, and one more location it is going to be for T. So in single address instruction, I load the accumulator with one data, add the accumulator content with memory operation directly, store accumulator will be having the result, again store back into the memory. So this is for one part of the expression. So the next part is C plus D. So this instruction number 3 to the remaining, it will take care of doing the summation. Then the final product will be obtained, and this product will be stored into the memory. So the one more category of this instruction is zero address instruction. So zero address means no need to specify any address. Okay. So if I am not specifying any address, how the CPU or how the processor will be able to understand the whereabouts of data. So whenever the address is not available, it means that it has to refer to only stack, and whenever we make use of the instruction push and pop, it is an obvious statement that push and pop has to refer to only memory. Again I refresh the point, stack. What is a stack? Stack is nothing but a portion of the memory which is organized in a different way as that of the normal memory, and in stack you will do entry and exit to the stack only through one end. Okay, and that entry and exit to the stack will happen by means of executing the push instruction and the pop instruction, push and pop. So I think now we will imagine the stack is available here, and the stack is expected to have some data. Okay, we can have some data. So now I will be having some A and then B. Now how it is going to operate? So as you all know, the stack will be always pointed pointed at the topmost element by means of the pointer called SP. So the stack pointer always points the topmost element of the stack, and entry into the stack and the exit from the stack is always going to happen only from one end. Whenever I want to enter something into the stack, then it is called as a write operation into the memory, and this is also can be referred as push. I am just going to push some data into the memory. And now if you want to take out some data from the memory, it is nothing but the read operation, and it is usually done by means of pop. So as and when we are executing push and pop, the stack pointer will be accordingly and automatically it will be adjusted. So now coming to the discussion of executing the expression, my intention is to execute a plus b, then star c plus d. So in that case, what should I do? I should first get b. Okay, so top of the stack could be either a or b. Now the view of the stack is given like this. Okay, so first I am pushing a. A will be getting and it will be entering into the stack and staying at the last location. After pushing A, then I push B, so A, and then on top of A, B will be sitting, and then I have to add. So when I want to add where the operands are available, both the operands are expected to be in the stack. If both the operands are expected to be in the stack, it is nothing but a memory, a portion of memory, and I no need to specify address. Why I don't need to specify address? Because the stack pointer is already pointing to the topmost location of the stack. So once I get into the stack, always I will be referring only to the topmost element. So whatever we have introduced as a variable, that can be pushed into the stack well ahead. So push A, that will push the data into the stack, and obviously the stack pointer earlier it will be in the 0th location, now it would have incremented, and the next operand also has to be pushed. So when I push again, the stack pointer will come to this position. So after pushing these two operations, when we just scan the expression, as we all already discussed in the previous class, A is an operand, so I will be pushing into the stack. Plus is an operator. So whenever I encounter an operator, immediately I have to take out the two operands. As far as this expression is concerned, we will be considering the brackets also as an operator. So let me just start with an operator. So this operator is nothing but a push operation. I need not do anything. A plus B. So A plus B means I will be referring to the data location A and B from the stack. Okay. So after loading this data A and B, it has to be added, and then I have to multiply with C plus D. So the first three instruction helps me to get the data ready in the appropriate registers, and then after doing this, then we are pushing C and D. So why we are pushing C and D? C and D are supposed to have some confidential data, so that can also be pushed into the stack. Then I can perform the operation what I am interested in. So add operation will perform addition on the two operands, whereas multiplication will perform multiplication provided the two expressions are evaluated at the beginning itself. Then we have pop x. So pop it is nothing but, so push means it is going to pull into the system, pop means it is going to take out from the system. So what happens? A and B, then it will encounter the operator, so it will apply the operator on A and B, so it will be getting some result as C. So this C will be again pushed into the stack. So pop x means the topmost element of the stack is going to be popped out. So with respect to stack, we will be always using the data register, and the data register is going to hold the data that is going to be popped out from the stack. And similarly, if we want to push something into the stack, the data has to be loaded into the data register. So without a stack pointer, the stack presence and execution may not be easily realizable. And the next topic of discussion is RISC instruction. So far we have discussed about how the CPU is going to be organized. So we have discussed it could be a stack based organization, it could be an accumulator based organization, or it could be a general register based organization. Coming to register based organization, again it is classified into two categories. One is it is going to refer to memory, or if it is not going to refer to memory. Coming to accumulator based organization, we expect one operand to be always in the accumulator, another operand it will directly refer to the memory. The answer will be consolidated and again it will be accumulated back into the accumulator. Now RISC instruction. So what do you mean by RISC? So we have two important terminologies in the computer architecture course. So one is called as RISC, another one is called as CISC. Of course, this will be expanded in the late coming slides, but now for understanding purpose I will say, so this RISC is nothing but reduced instruction set computing. Reduced instruction set computing. So to start with, we will see first is CISC, the characteristics, the advantages, then we will move on to RISC. So CISC characteristics, okay. So it was developed to make the compiler development easier and simpler. So in the previous discussion, we were saying that the compiler has to be intelligent enough to handle that particular category, whereas here if I just adopt CISC characteristics in my computers, then the compiler development could be easier and simpler. One important point we should remember, if I make the work of the compiler ease, the programmer will be taking the burden, and if I want to make a feel of the programmer to feel free, then obviously the compiler has to take burden. I cannot make both the compiler and the user to feel free. So as far as this CISC type of computers are concerned, it will make the compiler process easy, and also it will make the code also to be of good understanding. The full form of CISC is complex instruction set computer or it could be computing. So we have separate chips to make use of this particular facility, and many of the early computing machines were programmed only in assembly language, and the important point to be observed is in assembly language fixing the bug, it is going to be a big task, and the computer memory we all know it is going to be slow and expensive. And CISC was implemented in large computers, and some of the representation of this CISC type of category is available in PDP-11 and also in the DEX system. So the important highlights of CISC characteristics is it is going to deal with a large number of instructions, and the decoding of the instruction is going to be complex because it expects an intelligent compiler to handle it. Then instruction for special tasks is used infrequently, and then a large variety of addressing mode is required. So as such, we have explored different addressing modes in some class. So it can adapt to this type of CISC characteristics, can adapt to large variety of addressing modes, and also it offers variable length instruction format. Why it offers variable length instruction format? It can refer both the data in the stack, or it can refer one data in accumulator and another data in the memory. So in that case, it has to refer to memory for loading one data and also for storing the result. So all depends. So one point of observation is all the instruction formats need not be the same. It can vary. It can vary in size, it can vary in length. All that we need is it has to efficiently execute the work with the proper claim. So instructions are larger than word size, and instruction may take more than one clock cycle also to be executed, and because we have variable length, it cannot fix it. If all instructions are going to follow uniform length, then I can claim that it will be executed in a single clock cycle. So here in this case, because the instruction format is going to vary, that depending on the resources, depending on the requirement, there is a possibility that the execution may take multiple cycles. Okay, so instruction may take more than one single clock cycle, and less number of general purpose registers are only performed in the memory. Okay, so as far as the CISC characteristics is concerned, it will support only less number of general purpose registers, and various CISC designs are available to realize these registers for stack pointer and for managing the interrupts. So this completes the discussion of RISC characteristics, and the last topic of discussion is RISC characteristics. So as the name implies, RISC refers to reduced instruction set computing. So the coming to the characteristics of the RISC, it is designed to perform smaller number of types of computer instruction. When the number of type of instruction is going to be minimal, then this RISC category is going to be more efficient, and it can operate at a higher speed, and the claim made by the acronym is reduced instruction set computers. That means the instruction set architecture is going to support only minimal number of instructions. For example, if you want to perform addition, subtraction, multiplication, division, if I say that the instruction set architecture can support only 2 operations, obviously we can implement any multiplication by repeated addition and division by repeated subtraction. So here the claim is it can operate at a higher speed, and it is a microprocessor that is designed to perform smaller number of computer instructions so that it can operate at a higher speed. Okay, the same point we have mentioned already. And RISC instruction set holds less than 100 instruction, and it is used, it will always use a fixed instruction format. Okay, so because it is using fixed instruction format, it can adapt to, or it can recognize only simple few addressing modes. This is an important point. And then the use of register based instruction in comparison with a register based instruction, this method supports only few addressing modes. So here the compiler development mechanism, the load and store are the individual instructions for which through which we will be able to access the memory. Now coming to the highlights of the RISC characteristic instruction computing, we have simple instruction decoding mechanism and only very few number of general purpose registers, and because of that, because the complexity is not enforced on the instruction, it is going to follow simple addressing mode, and very few data types is going to be used or declared. And of course this will support pipelining also. So anyhow, we will discuss the terminology of pipelining in the forthcoming units, because it is an advanced level concept. I need not want to confuse that topic at this stage. So better you know what is RISC, that is reduced instruction set computing, how it works and what is the nature of that particular computing method, that we will discuss in the later sessions. And it will support only fewer data types, and it is very much suitable for pipelining, and one instruction, it will consume only one instruction per cycle. So it can always involve register to memory or register to register operation, and then the instruction format is simple, and execution time also will be faster, and it will end up in a small program to solve the same problem with the similar logic. Now we will just compare the real requirement of CISC versus RISC. So this has been tabulated. So if you understand each column, that itself will be a highlight for the particular feature of the particular category. Now we will just see one by one. So coming to the first point, it has a microprogram unit, whereas this has a hardwired unit. So microprogram, I think when we are discussing in the control unit design, we have discussed that how the CPU could be organized in the hardwired unit and the microprogram unit microprogramming. So coming to this classification, so the CISC is going to be the first to come, and it is always following the microprogramming concept, whereas in hardwired unit of programming, in order to reduce the CPU communication cost, we just made an attempt to increase the hardwire. The second point is the instruction set has various instructions that can be used for complex operations. There is no shortage in the instruction set architecture, it can have any number of instructions, whereas in this category, coming to the RISC category, most of all these instructions are very much primitive, and also the instruction set is reduced in nature. Next one is the performance is optimized with emphasis on the hardware. Here more emphasis is given on the hardware, whereas here more emphasis is given on the software. When importance is given on the hardware, obviously then the library, if we are going to depend on the hardware for the control unit design, it is going to be faster, but it will not be flexible. So the performance is optimized by giving importance to the hardware, whereas in the RISC category, more importance is emphasized on the software, and of course the performance can be attained with a flexible nature because it is in the software, but at the cost of time. Here we have only one register set, whereas multiple register set is supported in the reduced instruction set computing. And execution time is claimed to be high in this category, obviously here it is going to be very less. And the code expansion, so whenever I want to expand the code, it is not at all a big issue because we have only minimal number of instructions, so it is not going to make an issue, whereas here the code expansion is going to create a very big issue. And decoding of the instructions, because we have already claimed in the category it is complex, so definitely decoding of the instruction is going to be complex. It is going to give the burden on the compiler, and the compiler complexity is only going to be increasing, whereas here in this category the decoding of the instruction is made very simple. And one more important claim is it requires external memory for calculation, the CISC category, whereas the RISC category it will not require any external memory. And some of the sample processors that make use of the CISC category is System 360, VAX, AMD and Intel. So all these type of these brand of processors are going to make use of CISC category, whereas RISC category it is adopted in ARC, processor, alpha, ARM processor, and then PA RISC, and then Spark. So these type of processors will come under the category of reduced instruction set computing. And since the instruction length is minimal, it is going to complete the execution in a single cycle, whereas that is not going to be the case in the RISC computing. Instructions may take several clock cycles. And heavy use of RAM, so it can become a bottleneck if RAM is having only the limited size, whereas in the case of the RISC architecture, the RAM is utilized in an efficient manner, and hence the clock cycle also can be optimized, can be used in an optimized way. A simple standardization of standardized instruction is available in this category, whereas here we cannot standardize because the instruction length is going to vary, and of course this is efficient when we make use of the RAM. So this RISC more efficient the use of RAM than the RISC. Okay. Now a small number of fixed length instruction is available here, a large number of instruction is there in reduced instruction set computing, and we have only limited addressing modes, whereas the addressing mode itself is complicated, and as I told, the burden is going to be on the compiler part. So we have compound addressing modes, and important implications are the security systems and home automation. Whenever we want to improvise the efficiency of the security systems, or we want to automate the activities happening in the home by means of deploying some sensors, then this particular category CISC is going to be helpful, whereas it is not that much associated with this category, but still we can make use of the smartphones or the PDAs. Then the varying format, we have told varying format, to what extent it will vary, it may extend between the range 16-bit and 64-bit, whereas here it is always going to be fixed and it is going to be a only 32-bit format. And we have the concept of unified cache for instruction and data. Here we are going to maintain separate data and instruction cache. Maybe that I think it will be made clear if I just write an example. You all know we have memory, it is going to be the higher level memory. So before that we will be having the secondary memory. From secondary memory I will load into main memory, and then from main memory I have to load it in two cache memories if it is available. So one cache memory, here they have mentioned it as separated cache, that is what we have separate cache. So we have C1 and C2 as a separate cache, then in that case it is going to end up in a safe storage. Unified cache, and here it is using separate instruction and data cache, so it is otherwise called as a split cache. So you can just summarize the highlights of the advantages claimed in the CISC and the highlights and the advantages claimed in the RISC computer. So we have to analyze this two characteristics of computers based on the length of the instruction, the format of the instruction, whether it is going to be fixed or it is going to vary, and then whether it is going to support unified cache or split cache. So that also makes a problem, and how far it is going to follow the complicated nature of the hardware, whereas here it is going to exploit the benefits obtained at the software level itself. So this completes the discussion, the comparison of the CISC versus RISC. So in today's session we have discussed about the various CPU organization. Okay, to summarize, the CPU can be organized in different ways. So one important criteria for organizing the types of CPU is based on the number of addresses it is going to use: 1 address, 0 address, 2 address, 3 address, that is one category. Then how many operands are going to be present in the instruction itself, either it is going to be there in the stack or it is going to be stored in the memory or in the registers. Anyhow, these are the three possible locations of storing the data: memory, registers and stack. So people will always prefer stack operation, because by only two operations with respect to stack is push and pop. Okay, so we have seen stack based organization, register based organization, the number of registers supported by the processor that decides the efficiency of that particular organization. The next one is accumulator based organization, where we expect one operand already to be holding the operand, and you will refer to another operand either to the memory or to the register, do the operation, accumulate the result in the accumulator, then again transfer back either to the register or to the desired memory location. So we have classified CPU as 0 address, 1 address, 2 address, 3 address as one category, and another type is it could be register based organization or stack based organization and CPU based organization. So in stack based organization we are going to make use of only push and pop. In CPU we have some registers for handling the arithmetic and logic operation, and we have some instructions to transfer the data from one register or from register to memory or to memory to register. So with this the instruction format concept is over. So we will just resume with the next topic in the next session. Thank you.